So moving on to chapter 5, we're looking at radian measure. Okay, now the idea here is if you think about angles, I should just apologise again, I've got a rattly window in this room, it's very windy this evening, so apologies if you can hear some rattling. If you think about angles, what do we say? We say, well, we've got a full turn. If we start here and we turn all the way around, that is 360 degrees. And I don't know if you ever thought about it, but why 360, right? It seems like a bit of an arbitrary number. We could have split it up into 100 little sections, we could have split it up into 500 little sections, but why did we choose 360? Well, as far as I understand, the reason in history comes from the idea that the Earth moves around the Earth moves around the Sun in 360 days approximately, right? It's 365 and a quarter and a bit. It's roughly how far we move around in a year, right? If we move around the Sun in about 360 days. So that's the angle that we've moved around the Sun, and if you're observing things, if you observe the right things in the night sky, I wouldn't be able to tell you which, but I'm sure if you ask an astronomer that knows this sort of thing, there are some things that move around in the night sky once a year. So how far do they move from one night to the next? Approximately 1/360th. Now I don't know if historically the instruments were not good enough to make it a more accurate measurement, or if we just picked 1/360th as a sort of nice, neat approximation, but that's where I gather that's where we get the 360 degrees from, and I also gather it's from the ancient Babylonians who like to work in base 60. I'm sure you can look that up online and see if I'm right, and find out some more details if you're interested. But the point is, 360 is an arbitrary number, right? So can we have some sort of measure of angle which has something to do with the properties of angles or circles or something like that, because maybe that will tell us a little bit more, and that is where our radians come in. And here is our new unit of measurement for an angle, and it is this. You can think of an angle as kind of a section of a circle, can't you? All right, so if we have a radius here and we turn around this angle here, and we'll use theta for an angle, if I turn around so that the arc length that I've made is the same length as the radius that I've made, then that is called 1 radian. That's the definition of a radian, okay? So if you turn around a full circle, then this angle that I've turned around, this angle here, well, the arc length that I've made is 2 pi times the radius. So I turned around 1 radian, and I got 1 radian there, and another radian, and another radian, and I ended up having to go 2 pi lots of the radius around until I got back to the start, okay? In other words, 2 pi radians is 360 degrees, which is where we get our conversion factor, pi equals 180 degrees. So if you look at the first section of this chapter, that's all they're doing, is they're asking you to use those ideas, convert between radians and degrees, and the conversion is pi is 180 degrees. So when you end up with things like 30 degrees, well, that is 1/6 of pi, isn't it? Okay, because 180 degrees is pi radians, 30 degrees is 1/6 of 180, so pi by 6 is in radians is the same as 30 degrees, and that leads you to all those other things on the top of page 115 here. So we know things like sine of pi by 6, cos of pi by 6, sine of pi by 3, cos of pi by 3, and so on, because pi by 3 is 60 degrees. And that's really nearly it. I suppose that we should also deal with these things here because they're mentioned in the book, and these videos are specifically to look at this book. Now, this really is because the book is trying to get you to use these cast diagrams, which, as you'll know if you watch my other videos, I don't tend to use the cast diagrams at all. I go with it a different way. If you like the cast diagrams, I'm sure there's lots of videos out there explaining how those ones work. But we can prove these if we want to by just looking at the graphs. So I'll do the first one as an example, and I'm sure you can work from there. So sine of pi minus theta. Now remember, we're in radians. So pi is 180 degrees, so sine starts at 0 and does this. This is not now 180, this is pi. And this is pi by 2, and this is 1.5 pi, or 3 pi by 2, and this is 2 pi. So if this is theta, well, pi take away theta is this number here, pi take away theta. And you can see sine of theta and sine of pi minus theta are both the same thing. So sine of theta equals the sine of pi minus theta. Okay, so we can see it all from the graph. If I look for, let's go for the next example, where we have something like, we'll find the exact value of cos of 4 pi by 3. Well, we can do that from the graph as well. Cos starts at 1 and does this. 4 pi by 3, well, we know that this here is pi, this here is pi by 2, and this here is 1.5 pi. So 4 pi by 3 is pi and a third of pi, right? 1 1/3 pi. So 4 pi by 3 is 1/3 of pi above pi. Now that 1/3 of pi above pi, so if I use the symmetry of the graph, instead of going a third from this sort of bottom point of the graph, I go a third of pi away from this top point of the graph. Cos of pi by 3 is the same as minus cos of 4 pi by 3. Or in other words, cos of 4 pi by 3 is the same as minus cos of pi by 3. Okay, now that's fairly quick, but that is, you're used to doing this when the angles are in degrees. The only difference now is that instead of being 60 degrees, this is pi by 3. Okay, so cos of pi by 3 is cos of, same as the thing as the cos of 60 degrees, so that's a half, so minus a half is cos of 4 pi by 3. Okay, so we're just using all the tricks that we've used previously in trigonometry, only we're labelling our graphs in radians now instead of labelling them in degrees. That is, yeah, that's it for section 5.1.